In this video, I'm going to show you how to create a delay of 1 second, which is extremely high compared to the speed these devices are running. So I'm going to change this program, or I'm going to give you some information how to have a delay of 1 second high and then a high second low and so forth. And once you've got that information, you can actually go to generate delays of 5 seconds or 5 minutes or 5 hours, it doesn't matter. Okay, let's look now at using a prescaler and what the maximum times will be when I start at 0 and I roll over when I reach the count of 255. So I'm talking about maximums at this stage. If I use no prescaler and I start at 0, it will basically take 256 counts before it rolls over. Now each and every count, we've calculated that already. If it's a 16 megahertz crystal, is 62.5 nanoseconds. So to start at 0 and roll over at 255 will take 16 microseconds. If I use a prescaler of the clock divided by 8, that means it will take 8 pulses before my 8 crystal pulses before my counter or my timer will increment by 1. That means the new delay will now actually be 8 times without the prescaler, which is 8 times 16, which gives me 128 microseconds before it will roll over, which is now larger. So as soon as if I use a prescaler, my delay will become larger. If I use a prescaler of 64, then it will be 64 times without the prescaler, which is 1,024 milliseconds. If the prescaler is 256, it will be giving me a total delay then to start from 0 and then to roll over at 255 will give me a 4.096 milliseconds delay. And if I use a prescaler of 1024, then the total delay will be 16 milliseconds before it rolls over. Again, I'm saying if you start at 0, it will now take 16,384 milliseconds to roll over when it reaches the count of 255. So if I say I want to set up this timer of mine to have a delay of 10 milliseconds and I'm using a crystal of 16 megahertz. If I want to have a delay of 10 milliseconds before it rolls over, it's obvious that I cannot use a no prescaler or a divide by 8 or a divide by 64 or even a divide by 256. I have to make use of a prescaler of 1024 because this will give me a total delay of 16. So I want 10. So that means I'm not going to start at 0 anymore. I will start somewhere in between 0 and 255. And that's what I'm going to calculate on the next slide. I just want to also mention, as you can see here, we have a prescaler of divide by 8. We haven't got a 16 or a 32, but we've got a 64. We haven't got a 128, but we've got a 526. And we also haven't got a 512, but we've got a 1024. So it's all about the design that gives us the prescaler values. So we're going to look at the next slide now, and eventually I'm going to come up with a formula which shows you how to calculate the start point to get a specific delay. On this slide, I'm going to show you how to calculate a start point when you decide that you want to have a 10 milliseconds delay. And also we know at this stage that we're using a 16 megahertz crystal. So let's have a look at this. We saw on the previous slide that if you use a 1024 prescaler, then the total delay will be 16.384 milliseconds. And so if I want to make use of a 10 milliseconds delay, I want to start somewhere and I only want to get a 10 milliseconds delay, I must make use of a 1024 prescaler. I cannot use the previous one, which is 256, because that will only give me a 4 milliseconds delay. So that's not good enough. So this is why I have to use this one. So what I'm saying here is the required delay is thus 10 milliseconds. So that delay I'm now replacing with required delay must be 10 milliseconds. So that is still the 1024, the same 1024, multiplied now with a new delay, which I'm requiring. If I'm going to start somewhere and I want a new delay. So I'm just calling that K. So thus, I'm just substituting and say, okay, K will be 10 milliseconds divided by 1024, which gives us 9.7656 microseconds. So this is I want to start somewhere, and this is the delay that I want before this thing rolls over. And because this is the delay that I want. So now what we're going to do is I'm going to say the number of counts multiplied with, well, a single clock pulse should thus be 9.7656 microseconds. And that can now be calculated. So this number of counts is now 9.7656 microseconds divided by a single count time, and that gives me 156, which means I must in actual fact count in total 156, and each and every one of them is 62.5 nanoseconds, and that will give me a delay of 9.765 microseconds. Sorry. Thus, my starting point will be 256 minus 156 gives me 100, or hex 64. But what I've done here is I've actually calculated, I've done a few manipulations here, and I said that the start point is then 256 minus the required delay, the one that you want. If I say I want 10 milliseconds, this is where you will put it in. This is multiplied with a crystal. This is where you'll put the crystal in. This is why I've substituted that with 16 megahertz divided by the Prescaler. So this is a little bit of mathematics which I applied here, and you will see that this is going to work for each and every one. In other words, if I say I want a delay of, let's say, 3, and looking back at the previous slide, then my Prescaler can be 256. So I'll put 3 milliseconds in here, and in here I will put 256, still using the 16 megahertz. So this formula will then work for everyone. And in this specific case, the answer here is then 256 minus 156, which will give us an answer of 100 at the end of the day. So originally I've said that I want to get a 1 second delay. So when my counter starts at a specific point, in this specific case, the previous slides showed I start at hex 64 or 100, and then it will take 10 milliseconds before it will roll over. So, but my total delay I want is 1 second. So this 10 milliseconds, that was the required one from the timer, must actually happen 100 times, because that will give me 1000 milliseconds, which is equal to 1 second. So in my program, which I am going to show to you in the next slide, you will see that this rolling over will occur 100 times while my output is high the whole time, or while my output is low the whole time. So let's look at this program now, which will actually give us a 1 second high, 1 second low, 1 second high, 1 second low. So I started off with this program just to set the data direction, meaning I made pin number 5 on port B an output pin. That's also the same on the Arduino. And then what I've done here is I've loaded the start point, which I've calculated to be 100 or hex 64. It's a start point, and that will give me 100 milliseconds delay. It will start at this point. It will take 1024 pulses and after 1024 pulses it will increment by 1. So eventually it will take 10 milliseconds to roll over. So this is the start point. In this specific case, the control register A is just saying use this in the normal mode. Control B register, I made this 05. If you look at what's happening there, this is to activate Prescaler 1024 for this specific requirement. So in this green area here, I have basically said let's do this while the counter is less than 100. So it's going to do this 100 times, and this 100 here is actually that 100 which we multiply by the 10 milliseconds. So if I want a 2 seconds delay, I will basically multiply by 200 or whatever. This is just a counter value. So this is why I've said here, this is not the same 100 as this one that we reload here, or the same as that one there. This will determine the total length of the on time or the off time. Okay, so again here, like before, we're testing the overflow TOV0 flag, which is sitting in the interrupt register. So we're testing it. If it hasn't rolled over, as soon as I loaded this value 05, I started the timer. So I'll be sitting here actually waiting for 10 milliseconds to pass, and after 10 milliseconds the TOV flag will be raised. This will become false, and we'll increment the counter to 1. And what we do here is, again, like we did it before, this is just actually, it's a OR symbol here. I will again set it high or change it to high, but that will reset the specific TOV flag. This is just reloading the value again, because it has, once I move out of here, it has rolled over, so I'm just reloading it again. So it's going to sit in here, wait 10 milliseconds, increment by 1. Reload the values, it will still be below 100, do it again, and so forth. So it will sit here each and every time to get out of this 10 milliseconds, and eventually it will count 100 times that it will roll over. And if once it's rolled over 100 times, I will have a total delay of 1 second. What I'm doing here again is I'm reloading the timer. I will get out of this do section here, this do while, and I will reload my start point again with 100, because it would have been rolled over now. So this 100 and that 64 is exactly the same. Those two are exactly the same. So I will load that. I will reload my counter back to 0 again, and I will read my pin B, whatever it was. I will just exclusive OR it again, which means if it was a 1, it will go to a 0. If it was a 0, it will go to a 1. And after that, I will go back to the while one and redo it again. So if in the first green section the output was a high, in the next green section the output will be a low, and so forth. And this is how I generate a high 1 second, low 1 second, high 1, low 1, etc. And as I've said, if you want to have a delay of 5 seconds, you'll multiply by 500, and so forth. And this is how we can use timer 0 in normal mode to create a program which will do the requirement function. This is then the end of video number 4. Please look at the Atmel Studio programs, which will also be supplied.